So the kind of what I wanted to show you is from this book, Alex's Adventures in Numberland by Alex Bellows. I recommend that you purchase this book and read it. It's a very interesting read for anybody who is interested in mathematics or not interested in mathematics also. Maybe by reading the book, you'll develop an interest in mathematics because there are a lot of interesting things said in this. And I want to show you, demonstrate and read out a small section from this book, from this chapter. It's called Behold. And if you see the cartoon, you get an idea of what I'm going to talk about. It's of course from the ancient Greeks. So all of you must have heard of the name Pythagoras.
Yes, sir.
Yeah. So how do you know Pythagoras?
So he's a Greek mathematician.
Okay. So in those days, they like to call themselves philosophers, and of course, they also contributed to mathematics. What is Pythagoras most famous for?
So the
Does anybody know?
Pythagoras theorem.
For the
So the
Pythagoras theorem. Yeah, the Pythagoras theorem, which is that if you have a right angle triangle, then
all sides will be equal to 180 if you add them.
no, I don't know what you are saying.
I
But
thought it was
a square plus b square equals c square. That is the most famous thing, that is known as the Pythagoras theorem. That is, if you square this and you add it, square the length of this side and add it to the square of the length of this side, then you will get the square of the length of that side. So that is the Pythagoras. Yeah. And the proof, I don't know if you people have explored these things. Maybe that's another thing that I can show to you people. Basically, you get the proof by making squares with the length as the same as the side. So if you make the squares like this, then the area of this square plus the area of this square will give you the area of this square. Okay, so that is Pythagoras theorem. But today I'm not going to talk about the Pythagoras theorem. I'll talk about something else. So I'm reading from the book now. Says Pythagoras is the most famous name in mathematics, entirely due to his theorem about triangles. He is credited with other contributions though, such as the discovery of square numbers. Imagine, as was common practice, counting with pebbles. So they used to count with pebbles. Of course, we are going to use seeds. The Latin for pebble is calculus, which explains the origin of the word calculate. Okay, so the Latin for the word pebbles is meaning for the word pebbles is calculus, and therefore the word calculate comes from that. When you make a square array in which pebbles are placed equally apart in rows and columns, in a 2-row column square requires 4 pebbles and a 3-row column square requires 9. In other words, multiplying the numbers n by itself is equivalent to working out the number of pebbles in a square array with n rows and columns. The idea is so instinctive that the term square to describe self-multiplication has stuck. So basically what he's saying is, if you want to square any number, let's say 2, you know what is squaring, right? Basically multiplying the number by
multiply the number by itself.
Multiplying the number by itself. So if you want 2 times 2, you arrange it like that. And if you count out the number of pebbles, in this case seeds, then you get the answer to this, which is 4, right? Now let's do it for 3.
So 9.
Right? So if you do 3 by 3, 3 multiplied by 3.
9.
So this is how you get the idea of squares. Okay, so because technically it makes a square, so that is why the word square comes in. This is not what I was going to show you. So I'm reading further. Pythagoras observed some excellent patterns in his squares. He saw that the number of pebbles used in the 2 square, 4, was the sum of 1 and 3, while the number used in the 3 square, 9, was the sum of 1, 3 and 5. Okay, so just look at it like this. What he observed was, if you look at this and you kind of divide it out like that and like this, divide it out in the sense, make a division. This is 1, right? And this is 3, and it gives the same answer as before. Okay, maybe that's just a coincidence. So let's look at this. You can divide this again, 1 and 3, and what is how many are these?
5, 6, 5, sorry. 7 plus 3, 4, and 4 plus 5, 9.
Again 9. Okay, so does this pattern hold? Okay, any questions?
Yeah, that's what I was saying. How did he prove it? This patterns hold for every number.
It's not possible for every number, but he saw that this is a pattern. How to prove it, that's up to us. Okay, so now let's do it with a square of 4. Okay, and see if that is also true. You people can try it out yourselves also. You just have to, instead of using the beads, you can use dots with your pen or pencil and see if it is true. Okay, so is it true for every case is a question, but at least so far it seems to work. Why? Because if you do 4 by 4, we know the answer, 16. Okay, now let's try and divide it up again. So that's first set, second set, third set, and the fourth set. So count them out: 1 plus 3 plus 5 plus, that
So
should
the
be,
pattern is going like, so see, plus 2, plus 2, plus 2, 1 plus 2, 3, 3 plus 2, 5, 5 plus 2, 7.
no.
So I think it in the
Yeah,
another
but if
one
you,
in 5 by 5,
yeah, but if
it
you
would be
keep
9.
adding, yeah, so if you keep adding 2 to every number starting from 1, if you add 1 plus 2, you will get 3, 3 plus 2, you will get 5. What are these numbers called?
The odd numbers.
Odd numbers.
Oh, the consecutive
Yes,
odd numbers. Consecutive odd numbers.
consecutive odd numbers. And how many consecutive odd numbers? In this case, how many consecutive odd numbers?
Sir, 2.
2. In this case,
Oh,
how many?
2, 3, 4.
3, 4. Oh, then I sir I did 5 and 2.
Yeah,
So
it
you
would be
can do
5 consecutive odd numbers.
Yeah,
1,
so
3,
5
5, 7, 9.
5
So I
consecutive
think
odd numbers.
it would work for everyone.
It would work, right? You can easily see and work out a proof that if you keep doing this with every row that you add, so you add a column here and you add a row over here, that will make it 5 square, right? So if you add 1, 2, 3, 4, 5, 6, 7, 8, 9, you get the next odd number. And if you add 9 to 16, what do you get? 25. So that is 5 square. So in that way, see if you can now write down a proof that confirms this, that it will indeed work for every case. That will be very interesting to see.
The time